Gereon quick talk on some examples of non-algebraic classes in the BP network.
Thank you very much for the nice introduction, and thank you very much to all the organizers, of course, for the kind invitation. It's great to be here, and it's an honor and fantastic to give a talk to you. And so I know I'm not the final speaker of the conference, but I think I'm the last speaker who is not also an organizer. So I would like to use the opportunity to, on behalf of I think everybody who is here, to thank the organizers for bringing us all together and creating this wonderful atmosphere for doing mathematics. Yeah, so thank you very much. So what I'm going to talk about is an application of classical homotopy theory into algebraic geometry. And actually, many of the players that will play a role in my story have already appeared in several of the talks. So I'm going to kind of repeat some of the things, but well, I'm going to do it anyway and remind you of them to bring everybody on the same page. Something that will not appear, unfortunately, is Lubin-Tate spectra and Lubin-Tate rings. But let me say for the record, and also to Paul, that I do love them, but unfortunately I didn't know how to bring them up in this story. Okay, and so when I talk about algebraic geometry, then I will not derive anything, so everything will be plain and simple. For a general audience, I would have thought that would be a relief and a good thing. Here I'm not so sure if you if you like that, but anyway. Okay. So in many ways, anyway, this talk will be so effort-wise and maybe also otherwise on a downward trajectory, and make it. I'm going to try to make it easy, like until lunch break, and well, fill your time. Okay. So let me start. Oops. With a classical question. So Steenrod's problem, which asks if you're given some topological space and you look at its singular homology, can you realize any given class in the homology by a smooth oriented closed manifold? And of course, we all know that in Thom's famous celebrated work, he showed us or explained to us that the answer is in general no. And so the reason why I'm starting with this question is I hope we all agree that that's an interesting problem to think about. And my goal is to manipulate this question and a little bit also or like build on the ways on the ideas of answering this question and manipulate this question. And I hope that while I manipulate the question, you will just keep this warm feeling of agreeing that there's an interesting question that we think about, and then while I'm manipulating the question, you don't realize really that something has gone on, and you just keep on thinking it's interesting. Okay, so that's why I want to start with it. Okay, so the first thing I want to do is I want to pick, so I'm going to take this as my entry point, and then we could, for example, we could ask what happens if we choose a very nice space X that we start with. Maybe then everything works fine. And my choice of a nice space will be the solutions of a bunch of homogeneous polynomials with complex coefficients. And so, as you all know, they give us what we call a complex algebraic variety. And I'm going to require that it's smooth, so it's like even nicer. And I'm also going to require that it's a projective variety, so it sits in some complex projective space. And or you could just think of it as a compact variety. And we all know such a algebraic variety can also be viewed as a complex manifold, and actually as a very nice complex manifold. Okay, so then what else do I want to alter? Well, now I want to ask, or I want to look at algebraic subsets in my manifold, or in this algebraic variety. And what I mean by that, well, I just add some additional polynomial equations that this set has to satisfy. So and then I just get a nice natural way of forming subsets. And now that we have this subset, we can of course if this guy is smooth, so that's a condition on this polynomial equation that you can just check by writing down the Jacobian matrix, then you can associate a fundamental class to it. Yeah? So you just think of it as a complex manifold, and it has a fundamental, it's oriented as a fundamental class, and so that gives you a class in the homology. And then if you look at if you call J this inclusion of V into X, then we can take the push forward of that class and consider it in X, in the homology of X. Okay, so that brings us then to Horst's question. So if we start with this nice X, then we could ask, well, can we realize any homology class in the singular homology of this guy as now not as an arbitrary fundamental class of an arbitrary manifold, but as something that comes from an algebraic subset. Okay, so there are of course many things that should be said about this question. So first of all, I will just only show you how to get a fundamental class if you start with a smooth algebraic subset. But that's something that we can easily fix, because so in algebraic geometry you can always for any such algebraic subset you can choose a desingularization, so you can make it smooth, and then it turns out, so it's equipped then also with the birational morphism from this smooth guy to V, and it turns out then that, well, whatever, so in some sense you can take this guy as this side as a definition of the left hand side, but there are also many other ways of defining this this class in singular homology, and they will all be the same. Okay, so that's not a problem. In particular, we see that any algebraic, whatever we get as a fundamental class of an algebraic subset, is also automatically a manifold. Okay, and then there's of course another restriction that we should, or another thing we should say, that, well, these classes, they should better be of Hodge type. Otherwise, this question is, for obvious reasons, the answer is no. Okay, I'm not going to explain. Well, you all know what it means to be of Hodge type, and since all the classes that I'm going to consider in my talk will be torsion anyway, so that's not really a problem. Okay, so let's hop over that. But anyway, you all know that also to this question the answer is in general no. And Antti and Hitzbuch were the first guys to find to construct counterexamples. And the goal of my talk is, in some sense, to think a little bit about how they come up with a way to construct these classes, how to check that they are not algebraic, and I'm going to try to generalize this process. Okay, and so just not to sound too negative, so there's also sometimes there's a positive answer. So you all know that so Lefschetz's theorem on 1-1 classes says that in codimension 1 the answer to that question is yes, and just because it's well, if you wanted to prove, it's very easy to prove that fact. You could like sketch an idea by, if you start with a homology class, you look at its Poincare dual, and then a class in H2, where we can think of it as, so it's represented by a map in the homotopy category to the Eilenbecker mid-lane space K to Z, and it turns out that well, it's a very nice, or it can be realized as a very nice geometric space, namely the infinite complex projective space. And then since X is finite dimensional, it like factors through some finite CPK, and then you could think of taking CPK minus 1, so something in codimension 1, and take the pullback, and then you get some V which is of codimension 1 in X that gives you your class. Well, that's just a rough sketch. And the special thing is, of course, that so it's a very a special phenomenon that K to Z at K to Z is given by this nice algebraic space, a nice geometric space. Okay. Anyway, so in higher codimension things can go wrong. Okay, and so I'm not going to right away tell you how how Antti and Hitzbuch come up with their abstraction and what we can do with it. First, I want to alter the question a little bit and think about it as something that, or translate it into homotopy theory. Okay, and so the right thing, or the thing that we have to introduce to do that is the motivic homotopy category on algebraic varieties. And I assume probably all of you have seen that, but allow me to spend like 5 minutes on give you a very, very brief sketch on how you do that. Okay, let's start with complex manifolds, and let's ask the question, how do you do homotopy theory on complex manifolds? Of course, there are many, many ways to do that, and you could, for example, just think of them as a topological space, and then you have a nice homotopy category. But there's also another way, namely to use your Nader embedding and send them into simplicial presheaves. And the reason why that might be worthwhile doing is that, as you all know, presheaves remember. So if you look at, take the morphisms in this category, they still remember that you started with a complex manifold. If you had gone to topological space, we would just forget this extra structure. Okay, and then in order to do homotopy theory, we want to define the stalks, and for complex manifolds, it's a very easy procedure. We just define for every n n-dimensional, so n is like the complex n-dimensional stalk. You just take some balls in complex n space and then make the radius smaller and smaller and take the colimit over these guys. Okay, and then you all know that this gives us a way of defining weak equivalences in this category. Namely, then we can call a map between such simplicial presheaves a weak equivalence if all the induced maps on all the n-dimensional stalks give us a weak equivalence. Okay, and now that we have weak equivalence, we want to we can localize our category or invert these weak equivalences, and then we get the homotopy category of simplicial presheaves on complex manifolds. And a nice it's for this category, it's just a fun fact. Will play a role actually on the next slide. So that's why I mentioned it. If you take an open cover of a manifold, and then take the associated check nerve, and then look at the associated simplicial presheaves, then that natural map is automatically a weak equivalence. Okay, and so now that we have this unstable homotopy category of simplicial presheaves on complex manifolds, we can of course also stabilize it, and there are many different ways to do that. Either we can just replace simplicial sets by spectra, or we can also look at spectral objects in this category of simplicial presheaves. And then we get a nice stable homotopy category of homotopy category of spectra on complex manifolds. And stable with respect to, if you look at S1, so that's our simplicial set, and we just look at it as a constant presheaf, and smashing with it is invertible, as in the classical situation. Okay, so now I want to do this for algebraic varieties over the complex numbers. So we do the same trick. We send our smooth complex varieties into the category of simplicial presheaves. And of course, when I'm telling this story, so there are many, many names involved, and here's like a tiny part of the list. So there are many I've probably forgotten. I apologize for that. Okay, so the next thing we want to do, so on complex manifolds, we could just talk about open covers, and for algebraic varieties, we need to modify, or we need to find a nice replacement for open covers. And the way to do that is to look at Nisnevich covers. So we have already seen so étale maps, and of course you know all what that is. And so if you haven't heard of Nisnevich covers, and so it's something that is in between Zariski open covers and étale maps, and so it combines the nice properties of both of them. Okay, but you can also just think of an étale cover. Okay, and then in order to get a nice homotopy category, we want to localize this category of simplicial presheaves. And so we could also just define as before, look at the stalks, but it's like a little bit more annoying to write down the definition. So instead, we can localize that with respect to these check covers. So if we start with any Nisnevich hypercover, we can look at this natural map from the check nerve or check cover from to X, and we want to make all these maps into weak equivalents. And when we do this, we get a homotopy category of simplicity, or like one version of the homotopy category of simplicity for varieties. And in order to make this motivic, we also localize with respect to, we want to make the affine line invertible. So that the affine line here plays the role of the interval in topology. Okay, so that gives us then the motivic homotopy category. And then we can again stabilize this. And there are two versions, and Julie in this nice talk already reminded us of that. So either we can stabilize with respect to this simplicious circle as before, and then also take the Tate circle, which is given by A1 minus the origin. Or we could also just stabilize with respect to smashing with the projective line. Okay, both give us the same stable homotopy category. Okay, so now that we are equipped with this, with these categories, we can actually write down, get the map that I would like to study. I've already implicitly used this functor, so there's of course this topological realization functor that also Julie used in his talk, that if you start with a complex variety, you can look at the complex ones, so just the solutions in the complex numbers, and then you get a complex manifold. And for example, so P1 realizes into CP1, which is S2, so that gives us already a hint that we can also transfer this topological realization on our stable homotopy categories. Okay. So now, so just by extending this topological realization functor, we could, for example, start with some spectrum in this stable motivic homotopy category, take its topological realization, and then if you do the same for variety X, then we get an associated cohomology group in the classical homotopy category, and we also get an induced map automatically. Okay, and I want to think of this side as the algebraic elements, and this side of this side as the topological elements. And we have already seen an example of this map when I talked about these algebraic subvarieties or subsets. Then these guys are generators in the. If I start with the motivic Eilenberg-MacLane spectrum, then here's then motivic cohomology. Then these guys are the generators in the motivic cohomology, and then I can look at their image in singular cohomology. Okay. So now we can already guess what is my question. So I could either ask the question: so is every topological class every class on this side here, can it be realized as an algebraic map? Well, of course, the answer you can already guess that the answer would be no. So let me formulate the question then rather. So how can we actually produce classes in this guy here that are not algebraic? Okay, so that is the question that I would like to address now. And in order to do that, I'm going to explain to you how Atiyah and Hirzbuch came up with their obstruction or solution to Hodge's original question, and then I'm going to try to generalize this. Okay, so let's see how the Atiyah-Hirzbuch obstruction works. So let's assume we are given some algebraic subset V in X. Then we associated to it a fundamental class in singular cohomology, and one way of formulating the observation of Atiyah and Hirzbuch is that, well, we all know that there's not just one fundamental class okay, there's just one fundamental class in singular cohomology, but there are a lot of other cohomology theories that all have carry fundamental classes for a given subvariety. Okay, so for example, you could take a fundamental class, associated fundamental class in complex K theory, right? So whenever you have an oriented cohomology theory, then a submanifold will give you a fundamental class, and you could associate to V one of these classes. Okay, so Atiyah and Hitzbruch didn't formulate it in their paper this way, so they showed that. So they looked at the Grothendieck category of coherent sheaves on X, and then showed that there's such a class associated to any subvariety. Okay, but now when I mentioned so there's not just one fundamental class, where we all know there are many of them, and for example, we could also look at the universal fundamental class, right, in complex cobordism. And it was an observation of Bertotaros in the late 90s that well, maybe it's actually very interesting to also look at this fundamental class. And so when I write down these arrows here, so the blue one and the orange one, I'm cheating a little bit, because remember that if I could, in principle, I want to be able to start not just with smooth guys, but also with non-smooth or singular subsets. And then we took a desingularization of the subset. And in singular cohomology, it turns out that the choice of a desingularization doesn't matter, but in these other cohomology theories, the choice actually matters. And the reason to remedy this defect is to look at the an appropriate quotient. So the difference between two choices lies in this subgroup of elements in complex cobordism that come from something where you multiply something in the Lazar or in the coefficient ring with degree non-zero, and take all these guys together, and then if you so the difference between two choices of desingularization lies in this subgroup. So if you mod out this subgroup, then you get a well-defined class in MU theory. And the analog for complex K theory would take what is generated by the Bott element and mod that out. Okay, of course. So Atiyah and Hitzbruch didn't formulate it this way, so they used the Atiyah-Hitzbruch spectral sequence to do that. And you can think of this vertical map here as an edge homomorphism in the Atiyah-Hitzbruch spectral sequence. And but since Totaro used like this description, I just wrote it this way. But this is not the original way of.
Okay, no quick question. I'm a little
Yeah.
confused by one thing. Isn't beta invertible?
Yeah, you mean connected thing.
Yeah. Okay. Oh, yeah. Sorry. Yeah, that's a bad way of. Yeah. So.
You get a class in that group, but.
Yeah. Okay. So and then let's say connective K theory.
Okay,
Yeah.
sure,
Sorry.
great.
Yeah. Should have said. Yeah. Okay. Okay. So before I explain a little bit more about this vertical map, let me mention that this map here that we can associate a fundamental class in MU theory. That's actually it comes from a more or it's like an interpretation of the more general or like more conceptual way of thinking about it. So if we can also look at the algebraic or motivic tone spectrum, so the analog of that also already appeared in Julie's talk. And so then we have a tone map from this motivic tone spectrum to motivic cohomology. And so it turns out that if we also do the same trick, so we mod out this subgroup that is generated by everything that is. So the coefficient ring of this guy in diagonal degrees is also the Lazar ring, or MU star. So if we mod out the same thing as here on the right hand side, then we get an isomorphism. Yeah. So and you can also think if class of this guy was a generator here, then we can always we can always lift it here, and then there's of course this topological realization map from MGL to MU. So you could also write down this map this way. Okay, So now I just said that. So also Levine and Morel proved that this is an isomorphism, and you can think of this thing as something nice or like a good thing on the algebraic side, because it tells us that this quotient is also a cohomology theory, right? But you can also think of it as something bad is happening, because so we all remember that on the topological side, in general, this map, when we quotient out this thing, in general, this is not an isomorphism. So there are examples where this is neither injective nor surjective. And you could think of this as a bug, but you can also think of it as a feature, because, of course, the fact that this is not an isomorphism makes this whole story interesting, right? Because, so what we're going to do now, so the Adherzbuch, or the idea for the abstraction is, of course, that so if an element here wants to be algebraic, so come from some algebraic subset, it has to be in the image of this vertical map. And since this is not an isomorphism in general, we have actually a chance to use that this phenomenon. And the way we're going to exploit this is, as you all know, is like we're going to look at the operations that are induced by the fact that, well, there's some operations going on, and the fact that something is in the image of this map forces then the operations to vanish on that image. Okay, so in order to see this abstraction in action, let's introduce, well, you're of course all familiar with this guy already, so I'm going to look at the Brown-Peterson spectrum. So I want to look at, so as we should do at this conference, we choose our favorite P, and then we're going to look at the P local theory. So we have our Brown-Peterson spectra instead of mu. So you can also think of this is like the P local universal fundamental class. So you get the same type of abstraction. Then we can look at the quotient map on the coefficient rings, and so where we just look at all the generators up to Vn, and then we have the associated BPN theories. Okay, and I'm sorry. Since we can do this for every n, we get this tower of all these theories. I call it the Brown-Peterson tower. I'm not sure if that is the correct name for this tower. Well, anyway. So, and we also use as you are familiar with, so BP0 is just cohomology with P localized integers, and BP minus 1, I'm going to use this, or think of cohomology with FP coefficient as BP minus 1. Okay, so then what I'm going to use about these guys is that they sit in a stable cofiber sequence. So if you take the smash BPN with you take the smash product of degree, no, the suspension of degree Vn with BPN, and then so these guys sit in a stable cofiber sequence, and of course then we get an induced long exact sequence for any space. And so then if you look at if you take the toe map back to cohomology, then these maps here at the top, they correspond to the very familiar Milnor operations. And so you can, just to remind you, so you can construct them inductively or recursively. So you start with the Bockstein operator, and then take P's power operations and get these operations. And so the abstraction then, of course, works by actually looking at computations of the Milnor operations, right? Okay, so let's try to do this together. I mean, you all know how abstractions work, but well, I've prepared this nice slide, and I want to I want to use it. Okay, so we're starting with a class in singular cohomology, and now I'm going to look at mod P cohomology, and I'm going to want to find out if this class is algebraic. So it comes from something from the, well, it's in the image of this map from motivic cohomology. Okay, so what that means is if we can find this some algebraic subset that is sent to alpha. And what we just observed in this other diagram was that well, if something wants to be algebraic, then we can lift it well to a quotient of BP cohomology, right? And if we can lift it all the way up there, that means in particular we can lift it to a class in BP n-1, and then maybe also up there. And now we're going to use that. So this sequence here is exact. So that means if you can lift it here, then we can also lift it to one step further to BPN. And for that to be for being able to lift it, we need that. So the image must be 0 here. Okay, and so now you of course see how this the abstraction works. So now we're going to look at the image. So as I said, the corresponding image here is just a Milne operation applied to my class alpha. And now we see that if we know that something is non-zero here, so if we can compute the Milne operation on our class, we detect it's non-zero, then it could not have been 0 upstairs, right? So then this guy is non-zero. If this is non-zero, then because the sequence is exact, we cannot lift alpha n-1 one step further. And if we can't lift it to BPN, then we also can't lift it to BP all the way up there. And that tells us by this picture, so this obstruction coming from the picture that Levine, Morel, and Totaro gave us, we know that this class cannot be algebraic. So I call it the Levine, Morel, Totaro obstruction. So of course Attier and Hitzbuch should also be kind of mentioned there. Well, but it was like I couldn't fit it. It was like too long, all the names. So before I call it Attier Hitzbuch obstruction. So I hope that's okay then. And now I switch to this name. Okay, so everybody has been mentioned. Okay, so now I want to use this. So this is how this obstruction works. So now we of course have to prove that it's a non-empty, so that there are actually examples of varieties where we can find such classes. And before I move on to that and also generalize this, then the question, I want to mention something about, there's another way of obtaining this obstruction. And we have already seen, so there are also motivic cohomology operations, and that we have seen in Julie's talk. So there's the motivic Steenrod algebra. So let's say the mod P motivic Steenrod algebra, and there are corresponding Milne operations in that algebra. And so these guys live in. So as we all know, so motivic cohomology has always 2 degrees, and they live in bi-degree 2 times p to the n minus 1. P to the n minus 1. And so, well, as a cohomology operation, so they are mapped from one motivic cohomology group to the other. And now here's an important fact. So if you start with a smooth complex or like a smooth variety, then if you look at motivic cohomology in bi-degree ij, where I is strictly bigger than 2j, then this group vanishes. Okay, because you can, so these groups you can compare them to Chow groups, and then well anyway, so they vanish in degrees if I is bigger than 2j. And that tells, of course. Well, if you think of that as, so if we look here at the topological realizations, if we start with the smooth complex variety, so this guy, so where the image of the motivic Milne operation will land, it will just vanish, because so here we have degree 2 times, so 2i plus 2p to the n minus 1, and then I plus 2p to the n minus 1, but this is well, this guy is 1 bigger than 2 times this guy. So for for trivial reason, or not trivial reason, but for like a very general reason, the motivic operation just vanishes on everything. Yeah. In these degrees. Of course, they're non-trivial elements, so these operations do exist. But for this situation, they vanish. And then that gives me then, of course, also an obstruction if I look at the singular cohomology. If the topological min operation is non-zero, then you can't lift it. Okay. And that tells us also something about, so that's just an observation. So this Levin-Morel-Totaro obstruction, that's kind of it's particular to smooth varieties and bidegrees. So what do I mean by that? So of course, and you could think of, so they're not just actual algebraic varieties in the motivic homotopy category, there are also other objects, right? And for example, Eilenberg-MacLane spaces and so on that are not just algebraic varieties. And so if you look at other spaces, then this obstruction phenomenon will not work. And for example, you could just you could think of a trivial example, just take a fundamental class of an Eilenberg-MacLane space, and then the Milne operation will not vanish on that guy. But this you have an algebraic version, or like a motivic version of this fundamental class. Okay, so now back to our task. So now we are equipped actually with everything we need in order to address this more general question. So remember, our task was to find non-algebraic classes in some topological realization of a motivic spectrum. And well, I can't answer this question for an arbitrary motivic spectrum. So let's just pick a nice one. And since these Brown-Peterson guys have already appeared, so let's just pick one of those guys. So what about if we choose E to be BPN? And the good news is that so Brown-Peterson spectra, they also exist in a study motivically, and so there are many names that are associated to them. So since no talk should come out not mentioning Mike Hopkins, so here he is. And so I think Mike was the first one to consider like BP1 or like a connective, a motivic version of connective local p-local K theory. Okay, and also Gabriel Vazzosi and Hukris and Ormsby-Hoiwa and yeah. Well, many names are attached to these spectra. Okay, so now the question: can we produce non-algebraic elements in BPN? Okay, and we actually equipped with everything we need in order to address this question, as you can already guess. Okay, because so now I want to go back to this this cofiber sequence that we had, and these maps that corresponded to the Milne operations. And I'm going to exploit that. So these guys, they connect so different levels. So remember this was like a BP minus 1, this is BP 0, and then the next one goes to BP 1. So I can use these maps that come out of the cofiber sequence in order to walk up the ladder in my Brown-Peterson tower. And well, I can walk to whatever stage I want, and I can also always go back down to, remember, I can also use the tone map and go back to singular cohomology. And remember that the effect of this map here on the low horizontal line was just the composition of these Milne operations. So the idea that I want to use is, so I'm going to start with some classes in here, and I want to lift them all the way up, and then I want to use this like this obstruction here to test if something like still remained non-zero, or still remained a non-algebraic class. Okay, so what we're going to do is, so as I said, I want to compose all these maps little q's, so going from singular cohomology to BPN, and we also produced automatically an obstruction, right? So if I wanted to test that, if I send some class into into BPN or BPN cohomology, then we have already learned how to test if that guy is algebraic, because if this guy wants to be algebraic, it must be liftable also to the BP theory. And the way of checking that is like calculating the effect of the Milnor operations here. So this is like our test machine, checking that something is still non-algebraic, and this is the guy that will lift the elements. And the reason, so of course, well, I'm using this tool of lifting class. So this is not the most sophisticated way of producing classes, and there may be smarter ones. But when I started to be interested in this question, so there was no other well, I didn't see any other way. And in any way, it's not so trivial to write down. Well, maybe it's trivial for you to write down interesting concrete elements in BPN theory, and then checking also that they can't come from BP. Okay, so I'm just going to pretend. So that looks like a nice picture. Well, this is the obstruction again. But you will also have observed that we paid a price, right? So we started with something in degree k, and then we send it to something in the degree k plus, and then I had to sum up all the degrees of the VNs. So the degree of the cohomological degree increases a lot. So that's kind of bad news, because, well, in general, you would always like to have something where all the numbers are small, right? Small degrees, small dimensions. Well, not too small, they shouldn't be trivial, but anyway. Okay, but I'm going to claim that the price that we pay is as little as possible, because there's Wilson's unstable splitting theorem that was already mentioned in Jeremy's talk, and maybe also in other talks, and that tells us that so it's of course a much more general result, but one implication of it is if you start with any space y, then if you look at the map from BP theory to the BPN, then this map is surjective in all degrees less than 2 times p to the n plus and so on plus 1. So in a large range of degrees, this map is surjective anyway. And remember, in order for our obstruction to work, we need to find something that is not in the image of that map. So in some sense, so this BP was this thing, this monster that was sitting on the top, and so in order to find something non-algebraic, we need to hide from the monster that it can't see us. Right? And so Wilson's theorem tells us that, well, this monster sees a lot, but there's still some, of course, there's still some range left where we can hide. Okay, so concretely that tells us, if you remember that, so this number is connected to these degrees by that formula. Then if you want to produce something here that is not liftable to this infinite guy, then we need to pick k at least n plus 3. And I take k n plus 3 because it should be something in even cohomological degrees, otherwise it would be non-algebraic for trivial reasons. Okay, so I want something in even degrees. Okay, so now we have all this machinery, and now we need to prove that it's actually non-empty. So there is an example, or there are examples of these non-algebraic classes. And that's the following theorem that I would like to discuss now. So I'm going to claim that for every n, there is a smooth projective complex algebraic variety, and there is a class in BPN theory in this degree, which cannot be lifted to the motivic BPN theory. Okay, and in order to prove that theorem, so we have everything at hand that we need. So I hope that the way I told you the story makes proving this theorem now like a piece of cake. So we start with an elementary abelian P group, and that's also, so following also the idea of how Atiyah and Hitzelsbruch came up with their examples. And we take k copies of Z mod P. It works for any prime number. And of course, Wessner yesterday reminded us of, a similar group cohomology appeared yesterday. So we have some polynomial generators and then some exterior algebra generators. And these y are in degree 2 and x in degree 1. And we also know how the Milnor operations operate on these guys. So for y they just vanish, and then on the x's they send them to some p power of the y's. Okay, so now we just need to exploit this. So now we pick k to be n plus 3, so the minimal number that we needed in order to be okay with Wilson's theorem. And then we just take a product of these generators, and then you can just easily check that if you take the composition of all the Milnor operations, that guy is still non-zero. And so now then, remember the general procedure would then be, so we lift this class alpha then to a class in the BPN cohomology of this classifying space of our group. And then we know that, so then this abstraction tells us that this element in here can't be in the image of the map under BP, from BP. Okay, and then the last step is, so now we have to, so this was all on the topological side, so now we have to make sure that we can realize this BG guy actually as an algebraic variety. And there's a classical procedure to do that works for any finite group, and it's the so-called Godot varieties. And you can, so as I said, you can apply them to any finite group, and what you get then is actually a smooth, complex projective algebraic variety X, and this X is equipped with then a map of the underlying topological spaces to BG n plus 3 times CP infinity, and this map is highly connected. So if you're just interested in certain degrees of homotopy groups or of cohomology groups, then X looks the same as this guy, or whatever. If you have a map, if you have some element in this cohomology, you can just pull it back to X, and it will still be non-trivial. That's what I'm trying to say, I guess. Okay, so that's the proof of that theorem. So now let's look at the numbers. So I said that we pay this price of high degrees, and so what are the minimal dimensions and degrees that we can produce? So if p is equal to 2, if you take the smallest prime number, then the minimal complex dimension of X must be 2 to the n plus 3 minus 1. And the reason why it must be so high, that it just comes out of the Godot variety construction. So I'm not saying that this any variety that maybe that we can think of with this machinery of the obstruction, the dimension could in principle be smaller, but for this Godot variety construction, this is the dimension then that comes out. Okay, so if you look at n equals 1 and p equals 2, then so BP1 would be then local connective complex case theory, and then the smallest variety would be in dimension 15 and a class in BP1 8 of X. Okay, so now I'm already so this was like the main result that I wanted to present, and the main story that I wanted to tell. And let me stop with some or finish with some remarks on other examples of non-algebraic class. So, for example, first of all, if you look at the case n equals 0, then we would recover the examples of Atiyah and Hitzelsbruch. So it's really a generalization of their idea. And there are also other types of non-algebraic classes in singular cohomology that you probably, or some of you have have heard of. And so let me mention, so there also, so to complete the picture, so there are of course these famous examples of Jan Koller, who are of a very different kind. So he produced non-torsion classes. So the classes of Attier and Hirzbuch, and also the classes that I just produced, they will be torsion classes, and therefore automatically also of Hodge type. And so then for a while it was an open question, could this still be true for non-torsion classes, the Hodge question. And then he showed, well, even there are also non-torsion classes on certain hypersurfaces in four-dimensional complex projective space that are not algebraic. And these classes that don't disprove the Hodge conjecture, so which would be of course the analogous question with rational coefficients, something I forgot to mention, because an integer multiple of these classes will then actually be algebraic. And then Voisin, also based on Koller's example, produced another types of torsion classes. And what is, well, maybe non-interesting from our perspective, but interesting from other perspectives, that these classes, they cannot be detected by any locally constant invariant. Yeah, so in some sense they are not of, we can't detect them with any topological invariant. And the reason is, so they live in they live in families, and there's always a dense subset, these guys, where then there would be classes that in this family that would be algebraic. So any locally constant invariant can't detect them. And then very recently there were other examples by Olivier Benoit and Jan Christian Ottem, who produced some other examples on threefolds. And then there have also been other examples by Jagita and Pilutka, Jagita and Kamiko, and probably also other examples, who produce non-torsion classes for algebraic groups, but they all rely on the fact that so they pick some algebraic groups where Z mod P to the 3 is actually a subgroup in your algebraic group. And well, then a very nice class of examples were developed by Ben. So maybe the new feature that for his example is that he used the representation theory. And what is also interesting is, so for his examples, these Milne operations, they vanish, but there's a higher differential in the Attier-Hirzbuch vector sequence that is non-trivial. So there's some other operation that detects this obstruction. And well, after I put my paper on the archive, so then Kamiko used this idea of lifting classes and produced them with some more sophisticated calculations in the Attier-Hirzbuch spectral sequence to produce also non-torsion classes in BPN star of some algebraic groups. Okay, so that's all I had to say. Thank you.
Questions for Gereon? Maybe I should ask. Oh, sorry. Go ahead.
Can you go back one slide, please? The last slide.
This one?
Yeah.
Yeah. So I don't know. I always have to. Yeah. I don't know how much you need to.
Yeah, the last example. Sorry.
Yeah.
Yeah. So the last example, the non-vanishing of the higher differential in the Attier-Hirzbuch spectral sequence gives an obstruction.
Yeah.
So that means there should, if your class could be is algebraic, then there should be something that's lifted from this differential, which should be 0. Is that?
Yeah. Yeah. So the idea of using the Attier-Hirzbuch spectral sequence is, so you observe that if something is algebraic, then it must be correspond to a permanent cycle in the Attier-Hirzbuch spectral sequence. Yeah, and then so for Attier-Hirzbuch, they then just needed to look at the first page and take some quite simple differential that will vanish. They will actually correspond, and it's just a Bockstein plus yeah. And so then Ben showed then, So there you need some higher, like more complicated, well, not more complicated, but some higher differentials that are non-trivial on these classes. But it's the same reason, so it must be, class must be a permanent cycle if it wants to be algebraic, and then all the differentials have to be vanish. Yeah?
So do I understand it correctly that this kind of abstractions coming from this BP tower are all about kind of really like whether the class comes from an almost complex manifold, almost complex submanifold, or it's really kind of trying to distinguish between something which actually represented by an almost complex submanifold but not by algebraic subvariety.
Yeah, in some sense you could think of it that way. You mean because all classes in BP cohomology are represented by an almost complex? Yeah.
Did you have a question for me? Yeah.
Yeah, so so those classes are in VPN, right?
Yeah.
What happens for n equals infinity for the?
Yeah, that's a very good question. I forgot to mention that. So these I cannot lift them to, well, on BP the obstruction would just vanish, right? So I can I can test them anymore if the classes are still non-algebraic. So in some sense, so my method was based on the fact that you look at examples of varieties where the map from BP to like down to cohomology is not surjective. But you can produce. So we know that there are non-algebraic classes also in MU, for example, because in Collar's example, and also I guess for Voisin, those varieties, the map from MU modulo the subgroup is an isomorphism to cohomology. So for these examples, you know that that you can just lift these classes. They live also in complex cobordism. Okay, so that's the other type of phenomenon. But there you would use that the map from MU to cohomology is surjective, and for the other families you use that as non-surjective.
Okay. Well, let's see if lunch is ready for us, and thank Gereon again.